Okay, welcome again, everybody. Sorry for the technical difficulties in the beginning. Now we have the audio figured out, and we can start with the stream. So let me introduce ourselves again. I'm Stefan, a PhD student at the University of Cambridge. And today with me I have Eric, also a PhD student here. And we're here to answer all your questions about science, astronomy, cosmology, everything you want to know. Eric, do you want to say a bit what you're working on and what's kind of your area of research?
Again.
Yes.
So I'm a cosmologist like Stefan. My main focus is on the cosmic microwave background, which we see helpfully on the slide here. And this is this ancient light that was emitted just 300,000 years after the Big Bang, which is a relatively very short period of time. And we've used that to learn lots of things about the universe. Like it can help tell you how old it is, how much dark matter there is, and many more things. But there's hopefully more to come from the CMB, so that's what I work on.
Yeah, yeah, but maybe I should also say, like, I'm also working on cosmology, and in particular, I'm working on reionization. So how can the first stars turn the universe from a very neutral universe into an ionized medium? And yeah, so how this works is you can go on YouTube, and now in the stream chat, you can ask questions about anything you want to know, or you can go to slido.com and ask us questions there. And while we're at that, we'll take a few questions from the last streams because we couldn't answer them all. So let me just go back and take a few from there. One of them was whether or not dark energy plays a role in the very early universe. Do you want to say something about this, Eric, or should I?
I can say a few words about it, then you can fill in what I miss. So
maybe we should start by like explaining dark energy a bit and things like that.
Oh, sure. Thanks for the reminder. So currently, we see that the universe is expanding. All the galaxies and clusters of galaxies and so forth are getting farther away from each other. And when you look out into your observations, you see that expansion is actually accelerating, which when it was discovered was extremely surprising because you would expect gravity to cause it to slow down, right? You would think that things would pull towards each other and expand slower. That's not what we see. It's accelerating. And so those galaxies are going faster and faster away from each other. And the explanation we have for that acceleration is dark energy. There is some energy that causes it to accelerate. And in the kind of standard cosmological paradigm that we have right now, which is called lambda CDM. The CDM part is cold dark matter, which is about the other main unknown part of the universe. Maybe we'll come back to that later. And then the lambda part refers to this dark energy. So under that theory that we have right now, dark energy only really becomes important around redshift of a couple or something. Do you know what that is in time? I'm not sure.
A few billion years ago, so I don't know the exact time, but quite recently in cosmological terms.
A few billion years ago, which out of the 13, 14 billion year history of the universe is not so long. So the first answer is no, it was not important in the early universe. There are still problems with the standard model. One of this is this Hubble tension that I think we've touched on in previous streams. I don't know if I want to go into detail into it now, but it's a disagreement in different measurements we have of the universe right now. And one proposed solution to that problem, for example, is that there may have been an early dark energy phase where dark energy was important early in the universe, but that's not accepted yet. and we'll see if it is. And then there's also inflation, which is kind of like dark energy. Do you want to say a word about that?
Yeah, so I guess that's kind of the reason why the question maybe, well, made this connection actually a really good connection, because both dark energy and inflation have a very similar behavior. They have this, as you just explained, this exponential expansion. And they are not this, well, as far as we think, they're not the same thing. So we think that inflation was caused by what we call inflaton, something that made this expansion happen. And dark energy was caused by a different thing. This expansion was caused by a different thing, which is called dark energy. Although there are some models that try to connect them, but this is not very easy because they must be very different. And in particular, the density of the field that caused inflation must be much higher than the one that caused the expansion today.
And just to go back and define our terms really quick, inflation is this, a proposed period of very, very rapid accelerating expansion in the earliest phase of the universe, in the first small amount of time.
Yeah, very small fraction of a second, like a really small fraction, like 10 to the minus 30-ish, like really small. Yeah, right, good point. Yeah, and this inflation is actually really interesting, like kind of field of research. And actually, I think this is one of the kind of most mind-blowing things to learn when you like study cosmology, that basically everything in the universe, like all the big clumps of matter, basically all the seeds that later formed galaxies, are just quantum fluctuations that happened during inflation, that then got kind of blown up by inflation, and then kind of didn't disappear anymore because they were so large and were just big, like over densities of matter that formed and later caused structure to collapse into on them. So they later like formed galaxy clusters and other large structures that we see today. Okay, hey, there we get a question from Periscope. Did you hear about signs of possible life discovered in one of the planet's atmospheres? Yes, indeed. Thank you for the question. So there was a discovery of the molecule. What's the name?
Phosphine.
Phosphine, which is
one phosphorus, 3 hydrogens.
Yeah, I remember the chemical formula. I forgot the name. That was discovered on Venus, and one possible explanation for the existence of this molecule could be life in the clouds of Venus. So there was a press conference last week about this, where kind of the discovery was announced and kind of they presented all their work. And basically what they did is point a radio telescope at Venus atmosphere, well, at the planet in general, and look for kind of absorption lines of particularly molecules. And phosphine is one of the molecules that are kind of used as a sign of life in general, or proposed as like look for phosphine to look for life, because it's a molecule that's really hard to produce with normal chemical reactions, but could be produced with life. And so what they did is basically measure how much phosphine there is on Venus. And it's like, I think, a few parts per billion. I'm not even sure what the exact number is. But basically the point is, all the known chemical reactions that we know, like all the usual chemistry, the more exciting chemistry in the hot and dense regions, doesn't explain how we can get that much phosphine. So there must be some other thing going on. And either there's some new chemical reaction that we didn't think of before, or that we didn't know, or there could be something interesting like life on Venus. They even have a paper.
The geologists and planetary scientists think both things are very interesting.
Yeah. I mean, to be honest, I would find life much more interesting than new chemistry, but new chemistry is also cool. Yeah. And basically, yeah. Do you want to add something? Did I forget to say something?
So they note that this molecule phosphine is seen in, for example, Jupiter and Saturn, and they're the really, really extreme conditions that are in deep inside those massive gas giants can lead to its production. But as Stefan said, there's no known process that would do it on a rocky planet like Venus.
Yeah, you're welcome. How do scientists come to the conclusion that the CMB is near uniform in all directions? Do you want, or should I talk about the CMB? I'll open a picture.
Yeah, I mean, I can do it. So the CMB is the cosmic microwave background, right? So it's in the microwave. So you take your telescope, say, microwave telescope, I guess. That's not really a
Basically,
term
like
you hear very much.
like a big metal antenna that's like measuring microwaves. I mean, that's what they did in the beginning with Penzias and Wilson. Basically, they wanted to do communications and had like a big antenna that they wanted to use, to speak to people, and or I don't know what they wanted to do, the radio or whatever, some non-science, and figured out we measure signals. Okay, go ahead. I don't want to interrupt you.
No, it's fine. So yeah, you just take your telescope like any other telescope, and well, not exactly, but that's fine, and then point it at different directions in the sky, and the main signal at these frequencies, especially from a satellite, so if you can get away from atmospheric contamination and stuff. So this image is this Planck.
Yeah.
This image that we have here is from the Planck satellite that finished its mission a few years ago, and it'll just measure a single temperature on the sky from this background radiation. And if you look at all of the different directions on the sky, you point your telescope everywhere you can see, and you find that after you account for certain things like the movement of the Earth, then it comes out that it's very, very uniform. You see almost exactly the same signal from all directions.
Yeah, maybe I should point out the slide that I put up here is a very, it's like kind of a very high contrast. So in contrast is increased a lot about what you would usually expect. So when you take your telescope and point in any direction, you will measure 2.7 something Kelvin. And it's basically the same everywhere. So that's basically, there's not much to kind of discuss, like to kind of convert there. You just point your telescope and you measure, it's basically the same. And then what we did is subtract this number, so we get 2.72, I don't even know the exact number, do you know?
I don't remember the number, no.
Okay, 2.72 something Kelvin. And then this is kind of the average, and that's everywhere. You just point to everywhere, and always you measure the kind of temperature of this radiation is 2.7 something Kelvin. And actually, maybe I should say what the temperature is. So what we usually do is when we see some radiation coming from somewhere, we can often describe it with a temperature. And what we mean by that is, if there would be an object of that temperature, then it would send out that radiation. So the CMB, like there's not actually something that is 2.7 Kelvin cold. It's just the radiation that comes to us looks as if it came from something that's 2.7 Kelvin cold. So that's just a simple way of describing that radiation. And yeah, basically what you do is you take those two, the exact measurement, subtract the average, so there's 2.7 and a few more digits, and then the differences. So the difference that you see on this map are tiny, like a few parts in a million. Like this is a 0.000 something. I think like it's a microkelvin. I remember. It's a few thousand Okay, it's microkelvin differences. So the differences in the different directions are really small and it's almost uniform. And then you can do lots of interesting science with all those small differences.
These differences are very important, yeah.
Do you want to say about this something why there are differences, Eric?
Well, you already touched on it before. You want to expand on your inflation-y thing.
Ah, okay. So basically, I mentioned a bit earlier that you have some process in the universe that kind of introduces some random fluctuations in the universe. So we don't know how the universe looked at the very beginning, but we know there must be some quantum fluctuations based on our knowledge of quantum mechanics. And this just introduces some spots with more and some spots with less energy. And then naturally, the spots with more energy will be hotter than the spots with less energy. And then over the next few 100,000 years, there's a lot of kind of physical processes going on. So like radiation is, like kind of sound waves are propagating. So you basically have kind of a plasma of very hot material, and this introduces some structure. So this is not just random noise, but you see kind of spots have a typical size, for example. And you can measure all these properties, like what's the typical size of a spot, like what the kind of typical distances, etc., to infer how kind of physics worked in the early universe, or how these kind of space behaved from then to today, or how much matter is in the universe, how much baryons, etc. So that's lots of information.
And really incredibly, what you can do is if you take a big survey telescope, a regular optical survey telescope, and you look all over the sky and look at galaxies and mark down where the galaxies are on your map, then you can see the same scale in that galaxy map, the same distance scales that you can measure from this CMB map. So you can connect how those tiny density fluctuations that we're showing here track all the way into the galaxies that we can see today. Statistically, at least.
Yeah. Oh yeah, also greetings to Nico in the Periscope chat. So we got a few more questions for Reddit that I might go through in case you don't have any questions right now. We just check if there's anything on Slido or nothing new. Okay. So let me go here. Here's one question that mentioned that if we can, or well, asking if we can use the sun as a gravitational lens in order to take detailed images of the surface of Earth-like exoplanets, or in general to take more detailed observations or something. I'm not aware of anything like that this would be possible, and I don't think it should, because the sun is a very weak gravitational lens, and we can't use it to magnify anything. So what we can detect is that objects are very close to the sun. So let's say you have a star that's really close to the sun, and you're lucky to observe it during a solar eclipse. Then the position that you will see of this star...
Lucky, you planned very carefully and had multiple expeditions, but yeah.
Exactly, okay. If you go and observe that star during a solar eclipse that is really close to the sun, and make sure not to look into the sun, that's dangerous, you can see the position of the star, but not the real position, but the position is slightly off because the light is bent by the sun. But
very slightly, though.
Very, very slightly, yeah. You might not be able to see it. I'm sure you can't see it with the eyes. I'm not too sure what telescope you need. But it's possible in theory. But this effect is kind of small and it doesn't do any or like no significant magnification. So if you want to use lensing for magnification, which you can do, so the most distant galaxies that we have, as far as I know, at least the most distant stars, are measured, all of them, are measured, I think it's galaxies, or quasars, via a gravitational lens. So these gravitational lenses act kind of like normal optical lenses that you can imagine, like just if you have a lens in front of, like somewhere between you and the object, just that they're made out of matter, usually dark matter mostly, and they bend the light so it's brighter for you, like you can see it more easier. And this allows you to see objects that are further away than you would usually be able to. Okay, we got another question from Nico. What is, in your opinion, the most intriguing question that needs answer in cosmology today?
I should have an answer to this. You go first, I'll think about it.
I mean, the Hubble tension would be a bit of a boring answer, but I guess it's something that we should say.
If it comes out to be systematic, so regret it though.
Okay, let me go with the Hubble tension first. So the Hubble, let me explain what the Hubble constant is and why we want to measure it, and then why it's different. So the Hubble constant tells us how far is the universe expanding in today. So that's basically the number. The number is about 70 kilometers per second per megaparsec. So something that is 1 megaparsec away from us would be going away, like expanding due to the expansion of space with 70 kilometers per second. So that's really fast actually. And this is not exactly true for very close objects. Obviously the moon is not expanding from us due to expansion of space because we pull on it. It has gravitational attraction. Same goes for our galaxy and actually the Andromeda galaxy as well, because actually it's falling towards us and we're gravitationally attracted. But things that are far away, like far away galaxies, that are going away from us with a certain velocity, which corresponds to how far they are away. And you can measure this in quite a lot of detail by taking really far away objects, usually supernovae, and measuring how far they are away and how fast they're moving away from us. And combining these two things, you can measure how fast the universe is expanding. But then you can do the same thing with the cosmic microwave background. So you can look at the cosmic microwave background, measure all the sizes, and we discussed this a bit earlier about like you can use those fluctuations in the temperature to infer lots of physics, and this includes the Hubble constant. So you can infer what is the value of the Hubble constant from that, and what you measure from the cosmic microwave background is 67 kilometers per second per megaparsec. And from the nearby universe, like from supernovae, and you also use Cepheid stars for this, you get 73, 74 kilometers per megaparsec per second. So that's quite a big difference, and this is a bit illustrated on this left-hand side by this figure. Here we go. Basically, if we start in the late universe, late universe, so that's kind of today measurements, we find a large value, and if we go to early universe, we find like the value that we infer from the early universe that should be valid for the late universe doesn't agree. So there's kind of, if you build kind of a bridge of those values as a function of how far you array, they don't match up. So something is wrong. And that's a kind of big thing that just doesn't work out at all in our model of cosmology today. Yeah, it might be really, like, that might point us to a big problem in our cosmology, like in our model. Like maybe everything is wrong what we thought, but maybe also just the measurements of the one side are wrong, which could be, yeah. Eric, do you have something exciting?
It's a hard question. It's so difficult. I think I have to go back to the much older question of what are dark matter and dark energy, which might be hard to solve at this point. But
yeah, actually, I think that's maybe a more like fundamental question. Like this is more just, oh, we know the universe.
So this one is like a hint, right? This is this going to be, if it turns out that everyone did everything right and there's no mistakes, then is this going to help lead us to new physics, to a new understanding of the model, right?
Yeah.
Which is what everybody wants.
Yes. Yeah, I think that's actually a good point. Like kind of how you would, like what scientists would like and what would be more intriguing. Like this is more like, oh yeah, is this number, or this number? Like it's nothing. It's not like, oh, there's something we don't know what it is. It's more like, yeah, we are unsure about this number if you think about it. But then, as you just say, if this is wrong, we can like kind of find out, oh, why is it wrong? We can kind of debug the problem and like go further and further to find out what's going on with the universe. We know where to go, where to look.
One thing that's worth noting about the Hubble tension as well is that on the one hand, you have lots and lots of people working on both sides with new experiments, checking old experiments to work out, are there any problems here? And on the other hand, you have had for a while quite a lot of people propose many different solutions, and none of them is really
convincing,
satisfactorily explaining the issue either. So it's actually quite hard, it turns out, to come up with a theoretical explanation for this. And then you can work in the other problems that we don't need to get into, like the sigma 8 and I think there's another one. I'm forgetting one.
Yeah. Okay. So right, and what I wanted to say, right, the issue of kind of what is dark matter, what is dark energy, sounds like really exciting because, oh, there is something in the universe which is like makes up most of our universe, is making us expand faster and faster, and we have no clue what it is. But the problem is also we kind of have no clue. Like there's nothing, like we can just say, oh yeah, we just add a constant to our equation and it works. Like it could just be a constant, or it could just be something that doesn't do anything except be there and act as dark energy. Same for dark matter. It could just be matter that doesn't do anything. Like it could just be completely not interacting. Well, there are some theoretical problems with that, but kind of from the practical side, it could just be, oh, it doesn't do anything. Which does it has its own, no, it can't. I think there are problems with that. Okay, there are problems with that as well. So there are some hints for dark matter because the structure of kind of galaxies gives us hints about how dark matter maybe has to interact with itself, or maybe not. Well, there is a problem of this kind of core cusp. There's a problem of the kind of inner structure of dark matter galaxies, of the galaxies in general. so how the matter is distributed in galaxies. And if it would not interact at all with itself or anything, then you would expect kind of a cusp, so like a very peak distribution of dark matter. While what you may see in experiments is that the distribution, like there is not a big peak of dark matter in the center of a galaxy, it's more flat, more smoothed out, which is called core versus cusp, which arguably is a problem or not, depending on who you ask. And that might be kind of a hint of what dark matter really is.
I thought a lot of those problems were, well, certain people don't believe the simulation. So I'm not going to name any names.
Yeah, those are controversial, and yeah, it's not that clear if they are problems. Okay, there's one question we got from YouTube. What kind of astronomy instruments are in and around Cambridge? Are they used for research and training? So we do have a few telescopes in Cambridge, mostly historical ones. So they're like, there are a few historical ones, like the I think it's called Thorowood.
Thorogood, yeah.
Thorowood. Good. All right, okay, you got it with the names.
Well, I forgot the other one.
Okay, same for me. So there are some kind of historical telescopes. There's also a more modern one that we just call the 16-inch telescope. Does it have a real name?
No,
sure.
It's a 16-inch telescope.
Okay, which is a bit more modern, like it's computerized. But as far as I know, it's not used for any like very kind of cutting-edge research.
It's not used for any research.
Okay.
So, I mean, Cambridge is not ideally located for current modern astronomical research. Most of the big telescopes are on top of mountains in semi-remote locations, because you want to get away from bad weather, you want to get away from high water vapor and air, basically.
Yeah.
So we use ours for outreach, for student groups, the public, scouting groups, things like that. I will say that it is unfortunate that no part of the undergraduate astronomy curriculum here contains any observational component. We had that in my undergraduate. It was great, but that's all.
Okay. Yeah, so much for... I'm not sure. I think there is like one telescope somewhere in Cambridge which is occasionally used for some research. Although I'm not that sure.
News to me in that case.
Okay, we're not the perfect people to ask about that. But we probably will check that, and if we find out who's using telescopes for research, we'll get them to talk about that. We got 2 questions from YouTube about quantum fluctuations, 3 by now. Thank you for repeating the question. We saw it. We just wanted to go in the chronological order.
Oh. But before we move on, there's the radio telescopes.
Oh, go ahead. Yes, please.
So, well, I don't know that much about it, but not exactly in Cambridge, but not very far away, just a few kilometers away. There are several radio telescopes, which I don't think are... they're still being used. They're not the most prominent ones anymore, I don't think, but they're still being used. And then for radio, weather is less of a problem, I believe.
Yeah. I mean, you still don't want to have water vapor in the atmosphere for radio, but also for radio, you want telescopes basically all over. Well, for some applications, you want telescopes all over the world, so you kind of can't avoid the water vapor. Like you can't just all build them at high mountains close to the equator or something. So yeah, there are a few radio telescopes that are active that are not necessarily in the desert somewhere. And for example, in Germany, in Effelsberg, in the middle of the forest, where it's like not necessarily dry, there's a radio telescope which is quite active, and actually the second largest movable radio telescope in the world right now, as far as I know. With 100-meter diameter. Yeah, that's the advertisement. Back to quantum fluctuations. So I mentioned quantum fluctuations a few times. I didn't explain at all what that was, so thank you for asking for clarification. Eric, do you want to, or should I explain?
Be my guest. I'll fill anything in.
Okay. So one kind of aspect of quantum mechanics is what we call the uncertainty principle. And basically what it means is when you have some state or something in the universe, you can't measure its energy to arbitrary precision for a certain time. So there's some kind of freedom. That's kind of a bit of a approximate explanation, but quantum mechanics relies a lot on math, and I don't want to write equations here. So allow me this slight inaccuracy. And basically, what you can do, let's say you have a vacuum, even then you can't measure that the energy is exactly 0. So what can happen is that just a pair of antiparticle and particle get created out of nothing, exist for a really short amount of time, and then disappear again, annihilate. And that's what we call vacuum fluctuations. So basically, particles can be created and annihilate in the vacuum. And this creates basically fluctuations of matter everywhere. And the special thing about inflation is that there's a really, well, weird phase of the universe, because the kind of space-time where everything is happening in is expanding ridiculously fast. And if you do the math, or if you just do some hand-wavy explanations, you can kind of get that, okay, this rapid, ridiculous expansion combined with matter getting created randomly at some places leads to some matter actually being left over. Like, you actually get some regions in space where there's more matter than you would think if it would just all be homogeneously distributed, and you get some regions where there's less matter. And these are the fluctuations we are usually referring to.
As is often the case with things that start involving this kind of stuff, there are a few different ways to think about it, but the one I tend to prefer is that your inflation is being driven by the inflaton or the inflaton field, which is just some object that behaves quantumly, and then that thing can have little fluctuations because of this quantum uncertainty that Stefan was talking about, so that at different places it can have slightly different values, and then that can lead to inflation ending at very slightly different times in different places. And so if inflation's gone on for a tiny bit longer, then you're going to have expanded more in that little bubble and be less dense. And if it's gone a little bit shorter, then it'll be a little more dense. And that's one way I like to think about it.
Yeah, that's a point that I forgot, that basically when you have more or less of this inflaton, it also affects how long inflation will go on, which then affects like a lot. Okay. We got one comment about solar sails, which are cool. Yeah. Do you have any questions about solar sails? There's one question about the Higgs boson. So let me. Oh, there's another question about strange charm top and bottom quarks.
Oh, we got a particle physicist.
Okay. Let me open the particle physics slide and open the particle zoo, and also let me move away the chat for a second so people can see the zoo. So currently, physicists, we think that our universe is made up of these particles, all of these, plus dark matter and dark energy, of course, and yeah, something that makes gravity work. We don't know yet what that is. And these particles are the quarks, the leptons, and the bosons. Bosons are the things that we say they make the forces work. So they make electromagnetism work, they make the strong and weak nuclear force work, and maybe there's one that makes gravity work. And then there are quarks and leptons, which are what makes up everything. So everything, like, you know, the sand, this table, everything is made up of quarks and leptons. Mostly, well, I mean, everything's made up of atoms. Atoms are made up of atom cores and electrons. So there are electrons flying around. You see that's the kind of first item on our list, these electrons. And the atom cores are made up of protons and neutrons, which consist of up and down quarks. So that's those two. And basically, there exist a lot of more particles, which are not that easy to access. So when you have a particle collider and can smash stuff together and smash stuff together really hard, you can produce all kinds of stuff. And basically, we all found all of these particles. Actually, I'm not moving the mouse on the right screen. Sorry. Here up and down, and here electrons. And that's, well, everything else we can produce in particle colliders, basically. Or we can find them in cosmic rays coming from space. And let me just move off the chat in case anyone has a question. There we go. So let me answer the the second question first. Why can other particles kind of decay? Like, why does everything end up in up-down quarks and electrons in the end? And I'm not that sure about it, but I think the answer is that the strong and weak nuclear force, so the electroweak force, let's say for short. Okay, not sure. One of the normal forces, so not gravity, can convert these particles into each other.
It's going to be the weak force.
Okay. Yeah, so it's W and Z bosons, so yeah, weak force, you're right. For example, a muon can decay into an electron plus some neutrinos. And because a muon is much heavier than an electron, it's kind of much more expensive in terms of energy. So from Einstein's general relativity, you might remember that energy and mass are kind of equivalent. So having more mass kind of costs more energy. So it's kind of advantageous to convert heavy things into light things. So that's why you can convert, well, while muons decay to electrons, why tau decay to muons or electrons, why top and bottom decay into smaller things, and why strange and charm decay to up and down. And the reason why we still have multiple different ones left, and not say everything goes to electrons, is because there are certain conservation laws in physics that tell you that certain numbers have to conserve. For example, the lepton number is 1, which basically tells you can't convert a lepton into something that's not a lepton. Unless you have, let's say, a lepton and an anti-lepton. Then they cancel out and you can get something different. So that's why you can't convert electrons into, say, up or down quarks. There might even be more conservation laws, but that's one of them. And something similar works for the up and down quarks. So now, yeah, that's basically why they all get converted. And while we're at that, there's a question: how are antiparticles formed? So, okay, when I said this is everything that we know, I kind of lied because that's half of what we know. The other half is the same again, the antiparticle version, except for the bosons. So the quarks and leptons we have exact copies, basically with opposite charges that we call the antiparticle. So there's an anti-up, there's an anti-down, there's an anti-charm, anti-strange, anti-everything, anti-electron, anti-electron neutrino, etc. And they can be formed basically in almost all reactions. You can form antiparticles as long as you have enough energy, because an electron and anti-electron, they cancel each other. So you can just form out of a few photons, you can just form an electron and anti-electron, or a proton and antiproton, which is also what happens a lot in particle colliders. I'm not sure, like, if you're referring to that. So basically, that's how you can produce antiparticles. That's how they are formed. There's a different kind of question of how that works in the early universe and why there was more matter than antimatter, which I'm not going to explain now unless someone would like to know. I'm happy to, but it will take a minute. And let me finally get back to the first question about the Higgs boson. So I'm not an expert in particle physics, I should say. So I did study a bit of that, but I'm not researching particle physics. So the Higgs boson is responsible for a certain amount of the mass of particles. Not everything. There's something. So part of it is more complicated, but it's important in the Standard Model. Like, to make the Standard Model work and to make particles have mass, you need to have the Higgs boson, which, if I remember correctly, couples to all the particles. I'm not sure, but except the photon, right? Yeah, okay. it interacts with most particles, and well, the kind of popular explanation why it gives particles mass is: imagine a particle going through space, and just a massive particle. It's fine. It doesn't have to do anything, like, or kind of, let's say, accelerating. It would be like, okay, it could just do that. And now imagine the same, but you have lots of Higgs particles everywhere, and they all attract this particle. And when now this particle goes through space, it has to get past all of those Higgs particles, and this acts as if it had a mass. Basically, this causes a mass, you could say. So this is a very it's not the physical/mathematical explanation. So I can't give you the details on this question. That's more like the kind of popular explanation that I know.
And the Higgs boson is connected to the Higgs field.
Yeah, like.
Did they ask what field it was made by?
Okay. Yeah, basically, I think for every particle you just. I mean, let's not get into the details about fields now, because no, that's a good point, but I'm not at all an expert in there, so I shouldn't comment about that too much. Oh, that's a good question. Why do they have a neutrino? Well, okay, those are just all the neutrinos we know, and basically we can find them because reactions need to conserve the number of, was it the electron? So there's a conservation number associated with the electron, and it only has, like, it's only 1, let's say, for the, was it 1/2 or 1? I think it's 1. For the electron and the electron neutrino. So whenever you have an interaction with an electron, you have to have the same number of, let's say, electron things afterwards and before. So whenever you want to get rid of an electron, you need to produce an electron neutrino. So that's when, for example, a muon decays. You can have a muon plus an electron neutrino decay into a muon neutrino plus electron. So you always kind of have one electron and muon thing before and after, respectively.
I think something to note with these why questions is that, you know, all of this is empirical, it's observations, it's things that we've seen and then made up rules after the fact to explain.
Yeah, I mean, I just, you know, when I say, oh, it needs to be this way, it's just, well, our rules say, but our rules were made up after we saw this. So it's not like there is a reason necessarily, like why the rules.
The neutrinos were predicted before they were observed. So.
Okay, yeah. Because we made a rule that predicted them. Yeah, okay, it's a good point. It's a difficult question. Okay, where did I stop?
Sorry.
Okay, let's go back to right, yeah. Okay, so what I wanted to say about the neutrinos is there could be more neutrinos that we just didn't discover yet, which are not connected to one of those leptons. So there could be what we call sterile neutrinos that don't interact with the usual kind of particles. So there's an experiment that we can measure, that we can use to measure the number of neutrinos, but it only measures the number of neutrinos that interact with, I think, the weak force. So I think it's related to the Z boson. So all extra neutrinos that don't interact with the Z boson, or things that are like neutrinos, we would not be able to measure this way. And
I thought it was mostly W, but I don't remember.
Okay, it's W then. I forgot which one. One of the two
anyway.
Weak bosons. Yeah, and we found it's 3 there, but it could be that there are more what we call sterile neutrinos. Yeah. Oh, and why are the antiparticles there? Oh, wait, that's what we just discussed, right? No, that was a follow-up, what I mentioned with the Big Bang, right? Okay, so basically, we just mentioned at the beginning, we think, our universe began with something we call inflation, and there was the particle we call inflaton. We are very boring with naming particles, and at some point, the inflaton decayed into everything else, into all the other particles in the universe. And for some reason, it ended up, well, it decayed into matter and antimatter, because both were there. Then there is some reason why it made more matter than antimatter, because what happened at some point, like afterwards, in various stages, is that some of the antiparticles annihilated with the particles into energy and disappeared. And today we see there's just left over, like, there are really small amounts of antiparticles and mostly just normal matter. So that would tell us that probably there was just more matter than antimatter in the early universe, and all the antimatter annihilated, and that's what we see is just what's left. But we're not sure about that. Like, we can't explain this properly yet.
Well, more generically, that's not dependent on inflation, right? It doesn't have to come from the inflaton.
Yes.
As long as you assume that you started out with pure energy / equal numbers of particles, antiparticles, then you have to have some mechanism of making that not the case, of having an asymmetry.
Okay. We got a follow-up question about the fields. Do you want to say something about the fields? Because I'm not very comfortable in particle physics. So basically, okay, let me just say 2 sentences. So basically, in the kind of modern theory of particle physics, which is quantum field theory, all the particles are kind of fields, are fields that exist everywhere, but have excitations at some point. So you could have an electron everywhere, so there is kind of a field everywhere, but it's only excited at one place, which means there is an electron there. And then, yeah, like basically and then everything has a field, right? So there's an electron field, there's a field for all the quarks, for all the bosons. I think there's a field for everything, right? Is there something with multiple fields? I don't think so.
I don't think so.
So I can't go into much detail here because I'm not that well like versed in particle physics, and especially in this detail. But when we get the particle physics speaker, I guess at some point I'll ask them all those questions.
That'll be cool.
We got the question, why did the Big Bang take place? I think that's a very difficult question. We can't really answer the question of like why did anything start at all in the beginning? Like why does the universe exist? Like why did something happen ever? Really? Like this kind of, we don't have any like observations, any way of probing that. What we can explain is why did, say we have the infraton at some point, there is stuff in the universe, why did it expand? Like we can explain this, and basically this follows from general relativity. When you have enough energy in one place, it will, like in very simple words, enough energy in one place will lead to an expansion. But yeah, I'm not sure what exactly you're meaning with the question before I answer the wrong question here. Are electrons matter particles? If so, what do muons and taus do, and how do they interact? So yeah, all
muons and taus are basically heavy electrons.
Basically, yeah. So all electrons are matter in that way. So they all have some mass, and they're all like flying around, and they all exist in the universe, and we can measure them.
They all have an antiparticle.
Yes, good point. And they all we can measure them all. Same goes for quarks, by the way. They're also all matter. And so to talk about muons and taus, so one example of muons is they get produced a lot in cosmic rays, or they exist in cosmic rays. So kind of rays that come from outer space and fly to us, to Earth. They fly to the atmosphere, and those muons, like most physics students will know muons because they had at some day do an experiment and count all the muons that came out from space, which is, I think, what was it, 2 per cubic square centimeter or something? 2 per square meter? Something that order of magnitude per, what was it, per second? I can't remember it. I just remember the number 2. Should remember more than that. So yeah, you can measure those muons, and basically most of the interactions of those are, like most of the kind of natural ones are, they just convert to electrons and produce maybe some other like high energy electrons that then might produce, for example, a cascade of other things. One thing is IceCube. Let me show you IceCube. I do have a picture of IceCube, I think.
But basically, naturally produced muons and taus, and all muons and taus, decay pretty quickly into electrons, so they don't do much.
Yeah, true. And what we can, typically measuring muons we do with neutrino detectors such as IceCube, which is behind the chat, 1 second, which is basically a lot of photon detectors in the ice in Antarctica that just wait for like light to pass them. And basically we can see when, let's say, a muon flies into the ice and decays into electrons, those electrons produce like photons and all other kinds of things. And all this light that they produce, it's light, right? It's not Cherenkov radiation. No, is it Cherenkov radiation?
Cherenkov radiation is light.
Yeah, but okay. Anyway, okay. For some reason, with some mechanism, they produce light either through prior production annihilation or through Cherenkov radiation. In any case,
Cherenkov.
Okay, it's Cherenkov. Should be. This light we can measure with those detectors, and basically what you can see in the ice is like a track. Like you see kind of flash of light going from one point like through the detector, basically out to the other end, depending on if you have a muon or tau. And yeah, that's how we usually see them. That's a lot of questions. We have 3 minutes left, so let's just answer a few questions. And the next one we have to come back. The others we have to come back next week. Do you want to answer something? How and when will the universe end?
I am not an expert on this. there is a very active astrophysicist on Twitter called Katie Mack who has written a book about this that you can read about. One possibility that I'm most familiar with is the heat death. This is basically the idea that everything in the end, all the stars are going to die and everything's going to break down, and in the end, in a very, very long time, the whole universe will just kind of be one uniform temperature, nothing.
Basically, it's related. Well, I'm not sure if I should open the thermodynamics barrel now, but it's
No,
okay. Okay, we're not talking about thermodynamics here. Never mind. Go ahead.
And then there would be the possibility of a recollapse. So the universe is expanding right now, and it could collapse again, and maybe even bounce. I don't think that is seen as a likely phenomenon. I think the expectation right now is that dark energy is going to take over, and what already has taken over, and just accelerate everything out to infinity. But look at the book.
Oh, you're doing good advertisement here. Okay, let's.
She seems cool.
Yes. Actually, she explained a few bit of this. What was it? 2 weeks ago? 3 weeks ago? On this channel in the Cosmology from Home. Ask Me Anything. So if you want to check this out, you can go a few weeks back and watch that video. But we had also lots of questions we answered from lots of cosmologists. Okay, how do the neutrino detectors work? That looks like a question I can do.
It's on the slide.
Yeah. So basically, what you have is, well, what we detect is usually not neutrinos themselves, but photons that are produced indirectly by neutrinos. So first, I think we don't have any way. Okay, we do have ways of detecting neutrinos more or less directly. I think it's via nuclear recoils. So we see neutrinos interacting with some nucleus in, say, a really like cold and controlled environment, like in a big tank. I think like things like xenon might be. Are they sensitive to neutrinos? I think some of those experiments.
I don't know if they are yet.
Okay. Right. They will be at some point. I think sensitive to background neutrinos, like if they're getting good enough. So that would be kind of a more direct way. But the usual way to detect neutrinos is build something like IceCube, so like one of those Cherenkov detectors. And what they detect is neutrinos that convert to muons or taus or electrons, and then those electrons flying through the ice really fast. And what they actually do is they fly faster than the speed of light in ice. They don't, because they fly with almost the speed of light in vacuum, which is faster than the speed of light in ice. Note, they do not go faster than the speed of light, like the speed of light in vacuum, just speed of ice in that medium. But because they do that, they produce what we call Cherenkov light. And the idea is very similar to what you get when you have a, let's say, airplane that's going supersonically, really fast, and you get kind of a, well, the radiation, well, the, how do you call this? Basically the radiation you get from a particle gets enhanced in a certain way because you are going faster than the radiation itself in this medium.
It's like a sonic boom, but with light.
Okay, let's just go with that. I think that's the easiest explanation you will get. And basically, yeah, this gives you a flash of light. And this is a blue light you see in like nuclear reactors. Like when you go see on TV someone filming a kind of nuclear reactor, they usually show you the water where the old kind of rods are in, and it looks blue because this is a Cherenkov light. Like the particles coming out of those rods go faster than the speed of light in water, which produces this blue light, which is basically the same light you see in something like IceCube. So IceCube consists of hundreds of, it says there, I think it's 324. No, it's more, right? Oh, that's IceTop. Okay, loads of, 5,000. 5,000-ish optic sensors, so kind of cubes that detect light, spheres that detect light. Let's not get into the details of how they do that, but they can measure how many photons arrive at their position. And then you can just look at this whole 5,000 detector apparatus and see which detects light. And if you detect kind of light at some point and then shortly later at a different point, And then you can create a track where the particle went along, because you see light all around the path of the particle. And from the shape of this, you can actually measure what particle it is. So let's say you have a tau that gets created. It actually is so short-lived that it usually decays shortly after it got created. So let's say an electron, it would, oh, electron, not sure. I think a muon just goes through the detector, so you just get a simple line. I'm not sure about that, but I think it is this way. While a tau, it ends within the detector, so it decays into muons or electrons within the detector, so you see a line that ends at some point. Of course, it doesn't simply end, you get like a bulge or something, but you can differentiate between the different kinds of particles also from their shape in the detector. And you can measure their energy from how much light they produce. So those are kind of the most common types of neutrino detectors, so how you detect them. Okay, that's already our hour for today. Sorry for the technical issues in the beginning. We'll make sure that it doesn't happen again next time. Thank you all for asking the questions, and thank you all for watching. Thank you, Eric, for being here and answering all the questions and telling me about fields and stuff.
Thank you. It was a pleasure.
When you want to know something about more about Venus, there will be a whole live stream on this channel on Friday. So check that out. Telling you everything about Venus. Otherwise, we'll be back in 2 weeks. Monday again here. Well, maybe 1 week. We'll see. Follow us on Twitter. You'll get the announcement where we will be streaming again in 1 or 2 weeks. Monday, same channel, same time. And until then, see you. Have a nice evening.